So the first subject which I will tell today is Banach limit. So it is familiar from different courses. So what is this? Suppose we have a sequence, say xn. Just a sequence of real numbers, standard sequence. Suppose that this sequence is bounded less than some k. So all the terms of this sequence are bounded. Sometimes such sequence has a limit, sometimes not. So Banach limit is a way how to assign a meaningful limit to any bounded sequence. So we can define C. If you, I recall how it is treated in the function analysis, is the space of bounded sequences. C 0, the space of sequences xn such that limit xn when n goes to infinity is 0, no, in usual sense. So it is the sequence which go to 0. No, consider the space, say, xn plus r. So I'm sorry. C0 plus r. It is the set of sequences which go to 0 plus constant. So these are sequences xn such that there exists limit xn when n goes to infinity in usual sense. So this is now we have the norm in C and norm in C0 is the maximum or supremum of absolute value x in C0 is supremum module xn. So this is a Banach space, and if you assign to x is C0 plus r, assign limit xn and goes to infinity. Yes? Let's call it L of x. So this is a linear functional. So L of ax plus by equals a L x plus b L of y. It is a linear functional in this subspace C0 plus R. And the Hahn-Banach theorem says that this linear functional, yes, and I have to say, module L of x less or equal than norm x C0 plus x in C. So the limit is a bounded functional, and then the Hahn-Banach theorem says that such linear functional can be continued as a linear function to the whole space C from this smaller space C0 plus R. Okay? And this continued linear functional is exactly the Banach limit. No, it should satisfy additional conditions, which I will specify in 1 minute. The Hahn-Banach theorem itself is proved using usually uncountably many times the axiom of choice. Yes? So it is not so clean, and if axiom of using axiom of choice is sort of a sin, then this is theorem is all in sin, sinful theorem. In the construction of non-standard analysis, we also use axiom of choice, so we are equally sinners. If you are destined to use axiom of choice, you cannot avoid it, so you have to use it here or there, but anyway there is some place where you use the axiom of choice. And so I wanted to tell the proof of existence of the Banach limit by means of non-standard analysis. So, suppose x in C. Yeah, so x is a bounded sequence. For such x, we are going to define a functional Banach limit and this functional should satisfy the following natural conditions. The first is that linearity ax plus by equals a limit of x plus d limit of y. So it is the first condition. The second condition, module x less or equal than norm x in the space C, which is supremum module xn. Third condition is that if xn 0, if xn are positive, then limit of x is also a positive or non-negative. Third And there is also a fourth condition. That if you consider the sequence y n equals x n plus 1, so we just shift our sequence. Then one limit of x equals one limit of y. So it should not change if you shift the sequence. The usual limit satisfies all these conditions, so our goal is to construct this functional for all bounded sequences. So consider this sequence x xn, or it is n goes to xn. So it is a function x from n to r. It is just a standard function. And now let us extend our mathematical universe to non-standard universe. Yes, with infinite numbers. And then you have star x. From star n to star r. It is extension of our sequence. Now, first of all, for every finite n, every standard n, xn will be the same. So it is a true extension. Now let us take fix n some infinite n. Fix infinite n. And now just a minute. Here is condition 0. If limit xn exists, then for the sequences which have a limit, it should coincide with the Banach limit, so it should be continuation. Yes, I have to write it. Okay, so we fix some infinite n, and then we define limit of x equals x at this point n. N is infinite index, infinite number. So is x at this, no. Standard part of this number. And now let us check our all our conditions. So condition 0. Suppose there exists, say, a equals limit xn when n goes to infinity. It is a standard limit. What does it mean? This means that for any epsilon, there exists an k such that for all n more than k, module x n minus a less than epsilon. Yeah. So this is the definition of yes. Now this true for if you fix epsilon, then we have by transfer we have the following: for any k star n, there exists, just a minute, we fix epsilon, then you have the following, and corresponding k. So we take epsilon, we found k, and what happens next? Then transfer, we have the following. For all n more than k, you have module x n minus a module less than epsilon. Yeah. Now, in particular, our n is infinite, so it is more than this finite k. Yeah. So this means that x n minus a less than epsilon for any epsilon in R plus, I mean positive epsilon. So it is for any standard positive epsilon. Yeah. No, this means that xn minus a is infinitesimal if it is less than any standard number. Yeah? Now, if it is infinitesimal, this means that standard part of xn equal a, which is limit xn when n goes to infinity. This limit means the standard operation, standard limit. So we see that if a sequence has a standard limit, then this standard limit is the same as the Banach limit. So the property number 0 is valid. Next property. First, x n more equal than 0 for all natural n. Let me write x k, all k, because n is fixed there. By transfer, xn more equal than 0. Yeah. So this property also is good. Next property. Suppose that model xk less than k capital for all k in n. Yeah? Then by transfer, model star xk less than k capital for all k in star n. No, in particular, model xn less than k, because n is a fixed element, a fixed infinite element. So this property is also good. 3, it is linearity. So if you have two sequences, x, xk, y is a sequence of yk, then you have z k equals a xk plus b yk, and then this is true for all finite k. So by transfer, z start z n equal start a start xn plus b start yn. So we see that the nth term of the sequence z is also this means Banach limit of a x plus by equals a Banach limit x plus b Banach limit y. And now the last is invariance under the shift, and this requires to change a little bit our definition. of one limit, because this way, this definition is not perfect. If, for example, our sequence is, say, 1 for odd n and 0 for even n, yeah? So this sequence, its continuation will be the same, 1 for odd infinite n and 0 for even infinite n, yeah? And so if you shift this sequence, then instead of 1 will have 0, or instead of 0 will have 1. So this shows that this definition was not good enough. In fact, in some places we use this definition, yeah, and don't care how it behaves under the shifts, but this definition can be fixed. So consider prime. Consider the following thing. We will say the sequence xn. Consider the sequence xn prime. What is xn prime? We take the sum xk from n plus 1 to 2n and divide by n. So what is this? We take arithmetic mean of n terms of our sequence xn, yeah, starting from n number n plus 1 to n, yeah. Then we have the following thing. Let us consider yn prime equals x n plus 1 prime. So we just shift this sequence. So what we have the following situation, that yn prime minus x n prime, how to define it? We have to, it is 1 n sum k from n plus 2 to n plus 1 x k, yeah, minus 1n sum k from n plus 1 to 2n xk. And here almost all terms cancel, so this is equal to one n x to n plus 1 minus x n plus 1. Yeah? So just, yeah.
The last line is it 1 by n or 1 by n plus 1? Use x n prime equal 1 by n, summation of.
No. I take this sequence x n prime, and now I test this sequence. Yeah. So this is just shifted sequence x n prime. Yeah. I do not define it anew. I take the same sequence but shifted by 1.
Oh.
Yeah. And so just a minute. It is modulus, modul, and it is less than to k divided by n, because xk less than k capital. Yeah? Less than 2k divided by n. This means that if you define, so again, fix n star n minus n, and define Banach limit of x equals standard part of x prime number n. So n is infinite index. And so we can write for any k in n, we have that n more than k implies that model x n prime minus x n plus 1 prime less than 2k capital divided by k small. Yeah, I have to keep n for this fixed index. So for any epsilon, we have, if n more than this finite k, we have x n prime minus x n plus 1 prime less than epsilon. Yeah, because k can be done arbitrarily large. The standard k can be done arbitrarily large. And so we have, this means that x n prime minus x n plus 1 prime is infinitesimal, and the standard part of x n prime equal standard part of x n plus 1 prime. No, this means that limit of xn equals xk, limit of xk plus 1. So we can shift, no, if you can shift by 1, you can shift by any other finite number, the sequence, and we have the same value of limit. And all other properties are also valid without change. So this way we constructed, no, so to say, constructed, because our construction uses non-constructive elements like the ultrafilter. So it is construction modular some non-constructive elements. Yeah, no, that's it. I wanted only say that I myself used the Banach limit with success in my own work, so it is a useful thing even in the standard mathematics. So Banach limit is a good thing. Okay, now I wanted to tell another thing, another subject. another subject. It is example of a non-measurable set. I mean, not the best measurable set. It is important as a source of counterexample in the next topic, which is the non-standard measure and possibly a few words about non-standard probabilities. So it will be next time. So now here's an example. Example is the following. Consider the spec 0, 1, this set 0, 1, and I am going to construct not L measure. This means that some properties of Lebesgue measure do not hold on this, for this set. So every x, every standard x in this segment 0, 1, 0, 1. You know what? I will consider it as a circle. Yeah, so 1 is identified with 0. To avoid some non-necessary details, equals S1. So just a circle unit length. So this x can be written as a binary fraction, 0, and then x1, x2, and so on. Here we can have ambiguity because if x is binary rational, then either you have a tail of zeros or you have the tail of ones. It is two equivalent. Let us fix, say, on one hand, let us fix that in this case we write just zeros. Yes, no, why not? On the second hand, it is just countable set of such x, so anyway it should be negligible. So let me write, we neglect the binary rational x. Yeah. So in this case, we have this non-ambiguous string of zeros and ones. And now let us do the following construction. For any x, the set of such x is denoted B. Now, for any x is S1 minus B, yes, we consider it is a infinite sequence of zeros and ones. So it is natural to continue it to the non-standard. Yes, x star x. It is the map from star n, the just a minute, x is mapped from n to the set of 0 and 1. Yeah, for any index n, n goes to xn. So this is this map. So we continue it. Again, we extend our universe so that it is non-standard, and star x from star n to 0, 1. In general, we have to write here star 0, 1, which is equal to 0, 1, because it is a finite set. So any finite set, its image, star image is that set itself. Yeah, so we have this. And now let us take some n in star n minus n, once and for all x, for all x, and define x in A if and only if xn equals 1. Now you have to understand where we took xn, so let me return a little bit to basics. We consider the index set I, we consider the ultrafilter f, and you consider what is in this case star x. Star x is the following thing. Star x equals f from I to the set of n of pairs. Let me write f of I equals the pair k of I, x k of I. Yes? Now here k of I is integer. It is belong to n, and xk of I is 0 or 1. Yeah? So this first component, k of I, gives us its equivalence class. Consider equivalence class. MF. So all such functions which coincide with these functions, with this function on index set of indexes of measure 1. So MF and the first component k of I gives us some its equivalence class is non-standard integer. Yeah. F of I equals G of I, H of I. Yeah. So G mg equals K. Okay, M. Okay, N in star N. Yes, and H of I. What is H? H. MH. I'm sorry. MH. So H of I is the second part. It is either 0 or 1. Yeah. So if you have this, so we have a set of i's such that H of I is 0 and other set where there is 1. Only one of them has measure 1, other has measure 0 because we have ultrafilter F. Yeah? So it is almost everywhere either it is 1 or it is 0. 1 almost everywhere or MH of I equals 0 almost everywhere. Yeah. So this is where it is 0. It is the result. We have n star x. N equals 0 or 1 correspondingly. Okay. So this process, you see, is far from simple. It gives us for any x some either 1 or 0. Yeah, so if it is 1, we say that x is in A, and if 0, we say that x is not in A. And the claim is A is not Lebesgue measurable. No, okay, how to prove it? Let us consider a function. Say we have phi of x equals 1 if x in A, 0, x is not in A. Yeah? So this function is defined outside B, but B is anyway countable set, so it is negligible. Yeah. So this characteristic function of the set A, and now I want to prove that this function is this function is not Lebesgue integrable. So if phi A is Lebesgue integrable, then we would have the following thing. It is one of the numerals Lebesgue theorem. The following thing. Consider the averages of this function. Integral of from say z plus h phi a of s ds 1 divided by h, yeah, equals phi of s phi of x dx h phi a of hx, yeah. So it is the function which is averaged over the interval of length h, and this goes to phi a of x almost everywhere when h goes to 0. No, this holds for all Lebesgue integrable function. The function phi a is bounded, it is necessary, so it is integrable, it is bounded anyway. Now, this fun on one hand. On the other hand, let us see if, say, this set A is a set such that the digit number n is just 1, the set of such x is invariant under the shift over the 1 over 2 to the power n. Yes, one moment. Consider the transformation. X goes to x plus 2 to minus m. Yeah? So this transformation does not change the digits which are different from m. No, it can change the lower, but doesn't change not change x n if n more than m. Yes? Because what is this? We take this binary decomposition of x, and then we take the digit number m and add 1 to it. Yeah? If it was already 1, then it results in some reaction. We have to replace it by 0 and add 1 to the previous. If previous is 1, then we do the same. So we have some tail, but this tail goes left, and nothing goes to the right. So this means if n more than m, our n is infinite. Yes? So this is true for any m. Finite m. So this means that f of x is equal to f x plus 2 minus m for any m in m. So we have this. So it is invariant under the shift, and any such function, so if you compare this with this means that our function is simply constant. Yeah? Because a function which is periodic with arbitrarily small period is constant. Yeah, so fx is constant, fa. Now, if it is constant, and on the set A it is 1, then it is 1. Now, let us take the following transformation. Transformation. X going 1 minus x. Yeah, just symmetry. What happens if we do this transformation? If you take x equals 0, x1, x2, and so on, then after this transformation, t, we have the following, if you do it arithmetically, is 0, 1 minus x1, 1 minus x2, and so on. Yeah? And so this means that if somewhere was at some place 1, we have after transformation t we have 0. If it was 0, we have 1. Yeah. So in particular, we have ta equals S1 minus A. Yeah? So after this transformation, this set A goes to its complement. No model set B, which we should neglect because it is just countable. Yes? So, but T is just rigid motion. Yeah? It changes orientation, but it is rigid motion. It doesn't change the length. Yeah? This means that measure of TA equals measure of A. And now we have, if FA is constant, which can be only 1, because this function is 1 on the set A, then measure of A should be 1. Yes? On one hand. On the other hand, we have that A. Yes, from here you see that measure TA is measure A equals 1/2. Yes, because these two sets A and TA are complement to one another. So this is a contradiction. And it shows that this set is not, the set A is not measurable. I think that we have a usual example of which is usually considered in the courses of measure theory of non-measurable set. Do you know this example? So we consider the equivalence classes of x such that two are equal, x1 and x2 are equal if their difference is rational. Yes. Now we have a partition into this equivalence class, and take a set which has one term out of each partition. Yes, and then we have that all say the circle. It's better to do in the circle is a union of a countable number of copies of this set with some rotation. Yes. So on one hand, the measures, if they have a measure, should be added. So the measure of each of one is 0. Yes, because if it is positive, then the measure can be, or total measure can be 1. On the other hand, if they are 0, then the total measure should be 0 because the measure is countably additive. Yeah. So we have that example, and I think that this example has different nature. Yeah, so it is not a version of that example. Okay, so next time I wanted, next time at the end of the course we have all in all, I believe, 4 lectures remaining. Yeah, I wanted to talk about non-standard measures and non-standard probability, not as much as I can, so very little. And this can be a good counterexample in some constructions there. So let us do it next time. Okay, so let's finish.